Thanks for coming to this talk. No, I have one here if I need it. Thanks. I'm Richard Eisenberg, work at Jane Street, and we're going to be talking about something that we've done around the flat float array optimization. So we'll go through all. If you don't know what that is, that's fine. I'll explain that. But the big thing I want to say right up front is that this is collaborative work with Diana. If she had been able to attend, Diana would be giving this presentation here. So I just sort of want to give appreciation for her work on this. Okay, so here's what we're going to do today. Thank you for dimming the lights. Hopefully that makes that a little easier to read. We're going to talk about array representations in OCaml. Oh, by the way, I should also say that basically everything I'm going to be saying today is about stuff that is true both in OCaml and in Jane Street's extensions with OxCaml. This is an OCaml talk, definitely. We're going to talk about array representations, and then there's two problems that come from array representations as they are in OCaml. There's a runtime problem and a solution, and a compile time problem and a solution. So that's what we're going to be doing today. So first, background. So float arrays in OCaml have a non-uniform representation. And actually, how many people already know this? Okay, so about half of the room, that's fine. And then the non-uniformity, there's sort of two different problems that arise from that. So let's go through array representations for a bit. So this is going to be a little bit of education about this. Is just the current state of play in OCaml. So if I have an array of ints like this, that's what that looks like in memory, is that the variable ir is going to be a pointer to a heap block, and it's actually pointing to the second word of this block, not the first word of the block, because the first word of the block is a header. So here I'm just assuming 64-bit. It could be 32-bit, but we're just going to think about 64. So a 64-bit header looks like this. There's an 8-bit tag down at the bottom, and then some GC state taken up in 2 bits, and then the length of the block is the top 54 bits. And so for this I array, the tag is 0. The GC state is 0. Oh, does this pointer work? Yes, it does. So the GC state is 0, and then the size is 2, right? Because there's 2 elements. We don't count the header word when we say how many words there are on the block. And then the elements are, of course, that's the number 1, and that's the number 2, right? Because in OCaml, all integers are tagged, so that bottom bit is always going to be 1. So that's an integer array. Those are tagged integers, as I just pointed out. We can have a string array. And a string array looks like this. So once again, the header in my array is just the same, right? We have a tag of 0, and we have no GC state at the moment at least, and then a length of 2. And then we have A and B, and these are the actual string representations as they would be. I'm not going to get into string representations here. You can see the ASCII for A right there and the ASCII for B right there. Okay, so this is what we have. And importantly here, the elements in an int array are ints. The elements in a string array are strings, right? This representation for a string, that's the same that we would get if we just had a variable of type string. And this up here is the exact same that we would get if we had a variable of type int. Let's look at a float array. So here I have my float array. And this is a little bit different. So here in the float array, I have not the 0 tag that we saw for int and for string, but I have this other tag right there. Again, still no GC state, still a length of 2. And I'm not going to do IEEE encoding here, so I'm just going to have the floats as they look like that. But this is shorthand for a 64-bit representation of floating point numbers. On the other hand, if I just look at a float variable, if I have this variable f here, that is going to be a pointer to a heap allocated object. Once again, it has a tag. This tag is similar to this tag, but not exactly the same. And then it stores the actual float in its payload. And here, this just has a length of 1, because there's just that float, right? So in OCaml, if you have a float variable, it's always going to be a pointer to this heap object. Now, storing a float array like this is nice because it means that we don't have to use indirection. It means that if I have a big array full of lots of floats, this is a more efficient representation than the one I would get if each one was a pointer to a heap object. And yet, we're left with the fact that a float array is not an array of floats, right? This thing over here appears nowhere over here, right? This is in contrast to the string case. So like just as sort of pattern matching in the audience, right? This tag, just doesn't appear over here, right? So a float array is not actually an array of floats. That's what I meant earlier when I said that float arrays have a non-uniform representation. It's not the same as these others. So I want to explore how is this actually implemented? How do we get this fact? And so the challenge all sort of comes down to polymorphism, as the challenge always seems to come down to. Okay, so the first challenge in this is how do we construct such a thing? So we're going to have this function init that takes the length of the array, as well as a function that can produce successive elements of the array, and then that's going to populate the array for me. Well, this has to be the algorithm, and this is the algorithm that's used in that init. So the first thing is that if the length is 0, then we just return the empty array. Every OCaml process has one empty array of all types stored on the. I guess it's probably not in the heap, but it has this one thing. So we can point to that empty array if the length is 0. Otherwise, there's at least one element. So we generate the one element. We generate the first element, and then we have to look at it. If it's a float, good. Then we know that we can make a float array. If it's not a float, then we're going to make a standard uniform array. So this means that at runtime, we have to be able to look at a float and know that it's different from other values. So once again, when this computation, all of this figuring out has to happen at runtime, so we've lost all of our types. We have to just use these things that are available in these heap objects at the time. We can't just rely on types at this point. And so the fact that we need to make this decision on whether something is a float or not, that means that we must have a distinguished tag for floats, as we saw in an earlier slide. There we go. So that's this distinguished tag for floats, as I have been saying. Okay, so the other challenge is how do we index? So I'm going to look at get. Set sort of has all of the same properties, but get is just slightly simpler, so we'll look at get. So here, now, if I have an alpha array and I'm returning an alpha, well, a float array doesn't actually have floats in it. It has something else. So we have to do something special for floats. So we have to check, is it a float array? And if it is, then we're going to allocate a fresh float and return it, because if we're returning a float, all float variables are pointers to those float objects. And so we need to allocate a fresh one on extraction from an array. Otherwise, we're just going to return the element. So this means that I have to distinguish float arrays from other arrays. And so we have a special tag for float arrays distinct from other arrays. Right? So that has to happen in runtime memory. Okay. So now that's the background. This is true in all of your OCaml compilers. This is just sort of the way it is. So now let's talk about the compile time problem. I think that should be runtime. That should say runtime problem. That's just a bug in the slide. I'm going to talk about the runtime problem first, and then we'll do the compile time problem. These checks that we saw on those previous slides, that if it's a float, if it's not a float, they take time. And the compiler is quite good at optimizing these extra checks away when it can. If I know that I have an int array, if I've done some type inference and the type inference says that I have an int array, I'm not going to check to see, is it a float array? I know it's not a float array, it's an int array. But in some cases, I don't know because I'm in a polymorphic function, or I might have an abstract type. And if I have an abstract type, maybe it's float, maybe it's not float. We don't know, so we conservatively have to make these checks. So let's look at this in practice. Okay, so I'm using this website, godbolt.org. When I first heard of that, I was like, that's a pretty cool name for a website. It's actually just the name of the author. His name is Matt Godbolt. And the sort of the name of the service is the Compiler Explorer. So I find this a very powerful tool, so I'm recommending it out to people. But here I can choose one of quite a few different languages. Of course, I'm choosing OCaml. And then I can write some code, and it shows me the assembly created when compiling that code. So here in the code, I have this module which exposes an abstract type t, which under the hood is just an int. This is sort of a basic thing. But it means down here that in my extract t function, the compiler does not know that m.t is really an int under the hood. Because of OCaml's strong commitment to abstraction, at this point, maybe m.t is a float, maybe it's an int, we just don't know. And so that means that this extraction here, we're not going to know whether that's a float or an int extraction. Down here, in contrast, I've given a type annotation. I say this is definitely an int, so I'm definitely pulling from an int array. So actually, let's look at extract int first. So here is the code for extract int on the right. It's very nice. So what we do is we load that header word, right? We saw earlier with those pointers that we actually point to the first sort of payload word. And so I want to get the word 8 bytes before the one that's pointed to. So I load that from the RAX. That's where the parameter to my function is. So I go 8 bytes before that, and I load that into RBX, a register. And then I want to check the length. So the length of a block is in those upper bits. So I'm going to compare this against the number 1023, which is 2 to the 10 minus 1. So here, if the length is too small, if the length is 0 or less, I'm going to go to CamlML array bound error, which is good. My array has no elements at all, perhaps, and so I want to get an error. Otherwise, I just take the thing pointed to by the argument and then return that. Right? We return things in the same RAX register that first argument comes in on. Right? So actually, even though this is sort of low-level assembly code, it's not too hard to understand in terms of those memory diagrams that we had earlier. Very straightforward, nice and quick. If we look at extract t, on the other hand, there's a lot more work that has to be done. So here we do this, we still want to do the length check. That's still the first thing that happens. So that's all the same as it was before. But now, if the length check succeeds, now I have to take the bottom bits. I'll sort of use this AND operation to get rid of all the top bits, so I'm just looking at the tag. And then I need to check, is it the float array tag, 254? If it is the float array tag, we're going to jump down to this section here, and then this has to do a bunch of work, and it has to move the minor heap pointer, and it has to allocate some memory, and then maybe it has to call the GC. It's doing a bunch of work to allocate this float. This is completely dead code. This will never be run because I know as the programmer that m.t is just an int. But the compiler does not know this. And so that means that these extra steps are slowing down my program. Most of the time, we don't really care about it. It's an extra branch, no big deal maybe. But in some very performance-sensitive applications, we don't want to be doing this. And especially, we don't want to be doing this every single time we access an element from an array. That's pretty bad. Again, in some of our applications. So we don't want that. Okay, let's go back into the slides, hopefully. Yes, okay, so what are we doing about this? Key idea is we're going to label types about whether or not, or about whether they are definitely not a float. Right? The key question is this definitely not a float? If it is a float, we can expose that using equals private float, for example. So now we're going to do another demo. This one, I'm using this in our OxCaml branch of OCaml, just to show what we've done. Okay, so here's some code. Is that big enough for people to see? Yes, I see some nods in the back. Great. Okay, so right now, let's just sort of ignore the concrete syntax. We have a plan to fix this concrete syntax. But here I'm saying in my module M that t here, it's not any possible value. It's a value that is not a float. And so that means that down here, when I extract it from my array, I can use that same optimization that we saw earlier for uniform array access. So that's very nice. Oops, I'm in the wrong directory here. I want to be in the separability talk. No? What's it called? It is called separability. Tab completion is not working. That's fine. Okay, so I can show you that this indeed compiles. And if I change this to internally be a float, and then let's just not worry about this for now. I don't know why I'm writing that. And then now I try to recompile, then I get a complaint saying float is not float. Yay. So this is good. OxCaml is not integrated into the sort of the public version of Godbolt, so I can't show that the compiler, that the code generation is better so easily. But we can trust that that's actually happening under the hood here. And so that's what we've done. The mechanism here, if those of you, how many here are familiar with at immediate? Oh, I'm surprised. There should be, I would expect more people there. Anyway, the mechanism under the hood is quite similar to that, in that we sort of track essentially a kind on types, and that in the module subsumption check, we check that indeed this type here, this concrete type, definition for T, matches the specification. Okay, let's go back to the slides. Okay, so now let's talk about the compile time problem. So earlier we saw that there's this algorithm for construction. So this is what we have to do every time we're constructing an array. We have to go through these checks. Well, there's a certain assumption that's being made for the correctness of this little algorithm, and that is that the first element we get is representative of all of the elements that we will get from this type. Right? So because I'm only looking at that first element before deciding what flavor of array to get, it would be really bad if the first element that I get in an array is a float and has the float tag, and then others are not floats, or vice versa. So what we require is that every type that we might store in an array is either comprised entirely of pointers to heap allocated floats, or has no pointers to heap allocated floats. This property in OCaml is called separability, and it is a requirement of all types that we define in OCaml that they be separable. And there's a whole module in the implementation of OCaml just tracking this to make sure that every type is separable. Okay, so let's do another little demo. In this one, I am using the OxCaml compiler, but this one does not require OxCaml. Here we go. So here's a fairly basic file. I am defining an abstract type alpha t. The definition here doesn't matter at all. And then I'm making an unboxed existential wrapper around this type. So this at unboxed means that at runtime, this thing that I'm creating is just my alpha m.t. But individual elements of this type t over here might have different choices for alpha. Right? That's because it's existentially bound in this way. So if I try to compile this, I get an error. This type cannot be unboxed because it might contain both float and non-float values. Right? And that's because maybe I have one t, which is a float m.t, and another t, which is an int m.t. Both of those fit in my existential type here, but one of them is a pointer to a float, and one of them is not. This violates my separability condition. So the compiler correctly rejects this program. Right? If this program were allowed, it could cause seg faults. Because I could make one of these float, or I could make an array of these things, and then that algorithm would cease to work. Okay, let's go back to the slides. Okay, and I think I've sort of expanded this out here. So this is that same example. I've just sort of put a few more ingredients here to actually cause the problem. If this type declaration T toward the bottom were accepted, I'd be able to execute disaster, and disaster would say, well, the first thing is a float. So then it's going to look at the next thing and try to like unbox the float and put it in there. Goodness knows what would happen. It would be very bad. So this is rejected. Okay, yes, right, this is the problem. Okay, so what's the solution here? Key idea, label types about whether or not they are definitely separable. So here, if I know that some types are separable and some types are not, then the separable ones I can store in arrays. That's great. The non-separable ones I can't store in arrays, but maybe I can do other fun things with them, and that's fine. And so let's see, now we're going to do another demo in OxCaml. Okay, and then so here, what's it called? Non-float existential. So here I've changed this slightly, and I said that the argument to T must not be a float. And if the argument to T must not be a float, then the compiler is clever enough to know that actually this alpha m.t also can't be a float. Even though the actual definition of this m.t is not exposed, if the argument can't be a float, there's sort of no way to make the output be non-separable, right? Maybe every alpha t is a float. That's fine. But we can't have some mix of some of them being floats and some of them not being floats as long as we know that the argument can't ever be a float. And so we can't now expose floaty from my module. If I tried to write this, I can show you what would, well, first let me show you that this indeed compiles. Non-float existential. So this compiles. If I try to expose floaty here, then we get an error because I said that the argument to T must not be a float, and then here the argument to T most certainly is a float, and so it happily gives us an error. Interestingly, in the struct, I haven't said anything about a restriction on alpha, so this floaty down here is just fine, but I know that there's no way that I can expose this in my sig, because my sig restricts the kind of alpha. And so the compiler then accepts this definition because I know that T here is separable. And so I can't even mention floaty in my array because it's not exposed. And so that means that I'm not going to have a disaster anymore. Okay, let's go back to the slides. I think we're about to wind up. So this is all done in OxCaml. There's still a little bit more to do. I think we can do slightly better on separability, on tracking separability versus not separability in arrays. But what the real reason that we did this was not actually any of the things that I said. Those were the things that would apply in OCaml. The real thing that we're excited about here is that OxCaml also has a non-allocating option type, which was presented in this forum 1 year ago. And because that adds this extra element in, if I had a float or null, that's no longer separable, right? Because a float or null it's either a float or it's just zeros, and that means that I've broken the separability condition. And so we really can't have a float or null array, because that would be an array of non-separable things, but we would like other or null arrays. And so what we had for many months is that we couldn't have float or null, but we wanted to have that too. And so now, because of the separability tracking, we can move the challenge and say that we can't have float or null array, but we can have float or null, and we can have other or null arrays. We just can't have float or null arrays. Okay, so that's sort of the real internal motivation, and I believe that's it. Thanks very much for your attention.
We have time for questions. Just give off the mic to anyone discussing this. Oh, you're gonna give it? Yeah, sorry. maybe a silly question, but you show how when compiling we obtain the byte like the x64 code, right? So do these this selection only happens at the very late pass when you choose like actual instructions, or this is in some way in the intermediate stages, like intermediate representations of the code?
Sure, so let me just introduce Diana up here. So as I said at the beginning, Diana was unable to attend, but I know she wants to be a part of this, so I think I'll let her answer this question if audio is working.
Hi, Richard. Thank you very much. Yeah, the audio is working. I think there's an echo.
Hello, can you hear now?
Yes, I do. All right. Thanks for your question. Yes, the flat plot array application is represented in the midland, and it's actually dependent on a compiler setting whether to turn this flat plot optimization on or off. So it goes all the way to the like configuration tool.
Okay.
So I'm curious to what extent polymorphic specialization, at least limited forms of specialization, the compiler might do or could do in the future for float arrays.
Sorry, could you expand a little on what do you mean by that?
So you basically have two array representations, and array accesses have a branch in them to check which representation it is. Does the compiler do any specialization, generating two versions of the code?
Yes, it does if it's able to know whether some type is definitely a float or definitely not a float. And it does so in vanilla OCaml, and in OxCaml it also gets help from our annotations.
We don't ever sort of make two copies of the function. So if we know us sort of ahead of time which one it is, then we will specialize. But it won't make two copies.
I have a question. So when you introduce a feature like this, do you say, okay, now it's available, guys can start using it? Or do you ever say, let's automatically search our code base, see how many opportunities we have for this semi-automatically? Is it ever something that you do?
That's actually an interesting question. So for this feature, this is related to the unboxed option feature we were talking about. That unboxed is intended to something called what was it again? Richard, do you recall which library was it?
It was actually unfortunately a little hard to hear, but when we introduce something like this, we'll announce it. Some people will go and make changes. We'll also go out and search. It's sort of a combination of we'll find sort of the biggest spots where that matters, and then in the end, we have a lot of code, so it takes time to sort of find all the cases, and individual authors of their libraries will know best.
Let's thank the speaker once again. Thank you.